I hope everyone's doing well. Today I am Trish. Thank you for joining me for this video. The basicity of amines. We are looking over here at what makes an amine behave as a base and also as an acid, focusing primarily on the basicity of it. And everything will start here with this compound that you already know, NH2 ammonia. Amine is a alkyl version of it. What does that mean? You have a carbon atom attached to your nitrogen atom. An example, methylamine, CH3NH2. What does this R mean? It means rest of the molecule. Anything which is a hydrocarbon or a organic compound consisting of carbon for sure and other elements, it's an R group. Attached to an ammonia compound makes it an amine. Always remember, an amine will have pairs of lone electrons. Why would that be the case? Because of its valency. When you look over here, you're looking at a nitrogen, you have a hydrogen, you have a hydrogen, you have a hydrogen, and then you have this. If you were to eliminate one of these and attach it to an R group, which you know will be a carbon, it's no different than an ammonia, but it's being converted into an amine. So remember that. The basicity of amines depends on the electron density of that nitrogen. The electron density of that nitrogen is what will determine the basicity of that amine. If the electron density on this nitrogen atom is high, you will have an amine which is basic. If the electron density is less, it will be less basic, meaning it will be more of an acid than a base. Look at this reaction of how an amine can act as a base. You know you have an amine and you have a water molecule. These lone pair of electrons, they're available. They can pluck off that hydrogen and you can end up generating here an RNH3 plus OH minus. You see this? We started here with an amine plus water. We've got an ammonium, an alkyl ammonium, and an hydroxide. This right here is demonstrating the basicity of amines because here you're seeing a protonation. If you can protonate this, it means that this here is acting as a base. The amine is acting as a base if it can be protonated. The only reason why it can be protonated is there's enough of an electron density on this nitrogen atom for it to act as a base. Look here at this amine. How can we increase the electron density over here? Well, the hydrogen is irrelevant. This hydrogen is irrelevant. Your main item you're looking at is this. Anything which can donate electrons from this towards that nitrogen and increase the electron density over here will make this amine more basic. If you have something over here which is pushing electrons into the nitrogen atom, it is donating electrons in that direction. You're increasing the basicity. What are these type of R groups? Well, these are anything which are electron donating, like CH3. You have alkyl groups. Like example would be what this CH3 a tertiary butyl group, and here's your NH2. You have so many electron donating components, they can donate to this and increase electron density. Anything which is electron donating towards the direction of the nitrogen, you have a dipole in this direction, you're going to increase the electron density and this will act more of a base. These are the types of R groups which do that, which are your large alkyl groups or electron donating groups. It's not just limited to this. You can have cyclic compounds as well too. Consider this right here. You have over here a nitrogen and you have a hydrogen, and what you have over here is a cyclohexane ring. This is going to donate in the direction over here and it will increase electron density on that nitrogen and it will make it more basic. Consider also this. One of these hydrogens can be replaced with another cyclohexane group. Now you're having more electron density and this will act as a better base. If this nitrogen is surrounded by electron donating groups, this nitrogen has become more basic, meaning the amine will be more basic. Now you can consider the exact opposite. Anything which is sucking the electron density out of that nitrogen, it will make it less basic. In this given situation where you're donating electrons towards the nitrogen, these lone pair of electrons are available for protonation. Because they're available for protonation, it will act as a base, or it will be basic. If they're not available for protonation, then your amine will be more likely to behave as a acid, in which case it will lose a hydrogen rather than gain a hydrogen. It will not be protonated. In that case, if this were acting as an acid, it would be deprotonated. And I can show you a quick example. RNH2. Supposedly you're looking at it in terms of a very strong base. Now this is more likely to pluck off one of these hydrogens. I'll represent it better like this and this. In this case, this strong base is going to pluck off one of these hydrogens. And here what you will have is this amine acting more of an acid than a base, because it's being compared to something which is even stronger of a base, therefore it must behave as an acid. Here what you'll end up seeing is this RNH, you'll have an extra lone pair of electrons develop, negative charge here, and then you're this very strong base. I'll just write here VSB and then H. It has plucked off the hydrogen from the amine because this was a stronger base. In this particular case, this amine was acting as an acid. In this case right here, as I showed you before, if this is stronger than your other reagent and this is acting as a base, it will get protonated. Here it's getting deprotonated. If your amine is getting deprotonated, then it was acting as a acid. If your amine is becoming protonated and you're getting something like RNH3+, then it was acting as a base. Protonation is synonymous with base behavior. Deprotonation is synonymous with an acidic behavior for an amine. Let's close here with the opposite effect. I have something here on my R group which is sucking electron density, means these lone pair of electrons are not available for protonation. We're not going to see protonation, so here the amine is not going to act as a base. It will likely act neutral or acidic. But what can these R groups be, which can be sucking electron density away from the nitrogen and reducing the electron density here, or making the electron density higher here on the rest of the molecule? It could be something like this, C and then F and then F. You have all of these 3 fluorines attached to carbon, trifluorocarbon attached to your NH2. In this particular case, you have a strong electron withdrawing groups, very electronegative. They're sucking electron density. It's going to make this amine less basic, and it'll probably make it more acidic. So in this particular case, you have an R group which is loaded with electronegative atoms. You can even have oxygen, you can have a carbonyl group. All of these type of groups which have electron withdrawing groups can suck the electron density from the nitrogen and make it act as a weaker base or not as a base at all. Even you can have pi systems. What are pi systems or pi electron systems? We'll call these pi electron systems. These are like aromatic compounds. Consider this: if you have a NH2 attached to a benzene ring where you have aromatic compound, this benzene ring can suck electron density away from the nitrogen, and it would be less likely to act as a base. It can still act as a base, but it will be less likely to act as a base versus something which was not a aromatic compound. So pi electron systems, or if you have resonance stabilization going on, all of these things can suck electron density from the nitrogen. Those lone pair of electrons are no longer available for protonation. You would more likely see the opposite effect or no effect. When you have electron withdrawing groups, oxygen atoms, carbonyl compounds, pi electron systems which are like aromatic compounds, you can have resonance. All of these lessen the likelihood of your amine acting as a base, and more likely it doesn't act as a base, it acts neutral, or it may act as an acid. Look over here, dimethylamine, 2 methyl groups. These are electron donating to the nitrogen. They're going to increase electron density. These lone pair of electrons can actually pluck off that hydrogen from the water, and you can have protonation of this. Protonation is synonymous with a basic behavior, and you can see the CH3 and CH3, you've protonated the amine and you've added this extra hydrogen plus OH minus. This reaction is likely to happen, or it's foreseeable that it can happen, because you have a good enough ability for protonation, because there's enough electron density over here on this nitrogen for this type of reaction to occur. Focus over here. I have an amine aspect right over here attached to a carbonyl, attached to a carbon and fluorine. You have a lot of electron density being sucked away from here. These lone pair of electrons are losing their ability to be donated, and for protonation they're going to be sucked in towards this aspect of the molecule. Now if you were to react this with a water, you may not likely see what you're seeing over here, and the reaction may not take place. You won't have protonation over here at all. However, if you did this in the presence of a very strong base, and I'll just say a very strong base which is negative charge, now because this nitrogen is losing its electron density, these hydrogens are becoming relatively acidic. This right here will pluck off one of these hydrogens and it will take it away. Your end result here will be your very strong base has pulled off that hydrogen, and what will you be left with here is everything else. You'll have your CF3, which is this right here. You'll have your carbonyl group, and then you'll have over here NH You've lost that one hydrogen, so you've developed a negative charge here. So this reaction over here on the bottom is completed. Keep everything in mind in terms of charge and how everything should be balanced. Here you have neutral species on the left hand side, but here you have a positive and minus. They in their summation are neutral because they cancel each other. You have a zero here, you have a zero here in terms of charge. On this side you have a negative over here. On this side you have a negative here, so everything is balanced in terms of charge, so you always have to remember that. Here, because of the excess electron density on the nitrogen, it can act as a base. Here, because the electron density is being sucked away from these electronegative groups, it cannot act as a base reliably, but it can act more as an acid, and a very strong base can pluck off that hydrogen, and you can see the reaction play out. So the basicity of amines will depend very much on the electron density on that nitrogen. If the electron density is high, it can act as a base. If the electron density on this nitrogen is not high, it cannot be protonated, it will likely be deprotonated. And that right there is the end of this video. Thank you.